Hello world, this is Craig. As I mentioned in the last video, today we're going to look at Dave Dunfield's simulator for the Mod 8. So I showed you where that was. You go ahead and download that, unzip, and put it in a folder on your machine that has to be less than a 64-bit machine. You get a number of files with that. This is what it looks like unzipped. You get a assembly listing to a word format utility, which can really be handy. There's his 8008 assembler and the documentation for that. There's the Selby basic, and then hello world.hex is not part of his file. That's our hello world program that we've been working on. That's the hex result of the assembly, and we're going to be using that in the simulator, so I brought the file over. There's a listing to split octal utility, and there's the Mod 8 program, which is what the simulator, which is what we're interested in, and its help. And then there's a copy of the Monitor 8 assembly and a text version of that, and then a README file that describes all of this. To operate this, we're opening a command window, just like we're in now, and you simply type in Mod 8. And you get this window. Well, let's look at this window. This window on the left-hand side is showing us the address in the memory in the Mod 8 simulator, and this is just the resident monitor. So we can see if we went down and we looked through all of these addresses on the left-hand side, starting at 000 and on up, we would see that these are the commands in the resident monitor. So we're just looking at the resident monitor there. In the red, on the left-hand side, we see all of the registers. So we see A, B, C, D, E, the HL register pair, and the value of the memory location that's being pointed to by the HL register pair. So right now the HL pair is pointing to 00, and we can see on the first line on the left-hand side, the address value at 00 has in it 006. And so if we were referencing that as a memory location, we would be getting the 06, and that's exactly what's there. Below that are the flags. We can see we have our carry, our parity, there's 0, and our sign. And these are lowercase, meaning that they're not set. As soon as one of these flags is set, it'll go to uppercase. So on the right side of the red is our stack. And we can see we have all of our stack locations, and we have our stack pointer, which is represented by the little greater than sign. In the 8008, the only thing that we can put in the stack are going to be program counters for the return if we do a call or if we do a restart. So we will see that as we go through this simulation, the stack pointer will increase down and it will show us what it has left in the stack. On the right hand side, we have our memory that's being displayed in octal and ASCII, and if we wanted to, we could change this over and display it in hex, but we're going to leave this in octal for this example. If we want to just run this as if it were the MIL MOD8 running the Monitor 8, we would just type a G for go, and I have my caps lock on, so these are all going to be uppercase, and you're not going to see what I'm typing, so I'm going to have to tell you what I'm typing. But you just type a G, and it runs as if it's actually on the Mod 8. And so if we want, we can display the program symbolic, and we can say display from 000, 000 to 000, 100, and so it's displaying the resident monitor, the program, which is the resident monitor. And this just looks all the world for as the same as if it were actually the Mod 8 because it's running the Mod 8 code. And the only difference that I have found so far is that this is, orders of magnitude faster than running it in the Mod 8. That simple command in the Mod 8 would have taken it, several seconds to go through and display 100 or a couple hundred addresses. Let's go back to the command window, and the way we do that is you can see at the bottom we have got the 1, 2, and 3, and 4, and those are the function keys. So function 1 would give us help. So if I press F1, this is the help for the program in its current state, which is in its run mode, and it tells us what we can do. We press escape to get out of this, and if I press 2, it will completely clear this. If I press 3, it will stop the simulation and go back to the command mode. So let's press F3, and now we're back in the command mode. Just as before, if we press F1, it will give us the help for this window. And we can see that we're in the stop mode, the command mode. These are our options. We can display help. We can toggle octal and hex. The things that we're going to use the most are the G, which is the go. That's just a full speed execution. R, which is a reset, just as if we had pressed the reset button on it. S, steps one instruction. E, steps until a stack pops. So it steps until we get a return, or we're exiting a subroutine. So basically you can think of E as step until we get a return. N steps in a loop until we get back to that same program counter. L loads a Intel or a Motorola format hex file. And so rather than type in our program, our Hello World program from scratch, we're just going to use an L and load it in. So that's, a really convenient kind of thing. F4, 5, and 6, we've got a memory editor. We can change our memory. F5, we have a register editor. F6, we can set a breakpoint. F8, we can display our I/O. F10, exits. I and O, we can modify our input and our output port, which we're not doing in this. Okay, so let's escape to get rid of this. We're going to type a L so that we can load a program. We type a L, and it shows us in our current directory what we have there in the way of hex files. We have our Hello World, and of course this Windows version can't accept long paths, but nonetheless this works. Right cursor over to select that, and then enter to bring it in. It says 32 bytes were loaded at 010200. Since this was a hex file, an Intel hex file, as a part of that hex file is the address as to where that file should locate itself. If we had our program at 010200 and our data up at 010250, it would load both of those segments correctly. But this version of the Hello World is the last one that we left off, where we just had the data bumping right up against the bottom of the code, and so it's all just contiguous. We've loaded that hex file, so let's just go and let this run as if it were the MIL MOD8. So let's type a G. We can now do a XQT for execute. XQT. Oops, I got one off here. Let's do that again. XQT. We give our address, which is 010200. And there's our program. It just ran it. Hello World, that fast. Let's go back and to our commands and stop the program. Let's change our address using an F3. Let's enter the address as 010200. And you can see it changing up in the top. And here's our program. There's our LEI 017, load H, load L, LAM, ORI. We can use just the cursor and move down until we see our jump if false 0, and then our restart 0. The next instruction is restart 1, but remember that's not really an instruction. That is start of our data. The restart 1 is the same as the carriage return. So there's our carriage return, line feed, and then all of our data that it is interpreting as instructions, but it really isn't. And then that goes on up until we see our in 010236. There's our last carriage return line feed. And then it is the default, or what the memory had in it before, which is all zeros. In Dave's documentation, he says that he has the RAM at 070, but I have been running this 010 without any problem at all. So I think it just probably accepts anything that you want for RAM. Okay, let's go back up to our program, beginning. Now, we're in the stopped mode, and we can see if we look at our stack, it has left the value 003070 on the stack. The current program counter is at 000076, and you can see at the bottom the S equals 1. That's our stack equals 1. So we have one thing on the stack. Well, we have one thing saved on the stack and then our current program counter. And these other values for the program counter are all just values that have been there before. If we want, we can do a restart, and it'll clear that all out just as if we had done a fresh press of the restart on the MIL mod, and it's not going to hurt anything to do that. So let's go ahead and do that, and we get a reset, and everything just resets back to 0. Our program counter is back at 0. Now we want to run our program, and the way we're going to do that is we have to do it a little bit tricky because if we were to actually do a go, it would run real time and we could then execute our program. But we can't get back out of our program because our program does a restart. So what we could do is we can put in a breakpoint and then do a go and it would stop. Or we can put in and just change the stack pointer to our program and then tell it to start the program from there in a single step mode. Because that's our goal. We want to go and single step through our program. So let's do it that second way, where what we're going to do is change a register. So I press F5. It says which register we would like to change. We can change all the registers, including S is the stack pointer and P is the program counter. We're going to press P to change the program counter. Going to change our program counter to 010200, which is where our program is. And so you can see here on the stack, we're pointing to the 0th entry in the stack, and that's our program counter, 010200. Let's exit out of this little menu by pressing the escape. And now let's change our address that we're looking, and let's change that using F3 to where our program is, and that's 010200, just so that we can see our program at the same time that we're running it. Now we will want to do just a single step. And the way we single step is we press the S button. This is the very beginning line of our program. We have the LEI 017. Let's look at register E. Register E right now has 0 in it. As soon as we execute this, we should have 017 in register E. So let's do a single step down, do that instruction, and now we can see that we have a 017 in register E just like we expected. This next instruction is going to put a 010 in register H. Right now H is 0. Single step now, we have a 010 in H. This instruction is going to put a 221 in register L. Register L is 0. Single step now, 221. Now we have loaded the HL pair. The memory has a valid now. Memory is actually pointing to something now. It's pointing to whatever is at 010221, and that's where we put our data table. If we look at our program, here's our program at 010221 is the beginning of our data. So that's what we expect right now. 010221 is pointing to that value that contains 015 in our memory. All right, now we're going to take that data, the 015, and we're going to load that into register A. So we look at register A right now, it's a 0. We're going to press a S to execute that instruction, and there it goes. It took whatever was in register M, which once again is really not a register, it's just a memory location that's pointed to by HL pair, and it put that in register A. The next instruction is where we had to set the most significant bit to 1, because when the restart uses that, it uses that as the start bit, basically. So we have to set that to 1. So we ORed it with 200, and we do that next step, and now we see that A is 215. That's great. We now put that into B because B is where it is required by the monitor to output it. There we put it into B. And now we're going to do a restart 2. Now restart 2, which is restart 020 also, same restart. That is the restart that is going to output this character to the monitor, or to the display. Let's go ahead, and this time only we're going to enter that restart 2. So we're going to single step into that and let it go into that restart just for the education, basically. So we press S again to go into restart 2. Watch what happens. First thing it does is it put the next instruction onto the program counter, which is 010213, and then it jumped the program counter up to where we want to go, which was 000020, and you can see that that's now where we are on our stack. That's what the program counter is actually pointing to. When we want to go back to our program, it will pop that 010213 back into the program counter and take off from that. So right now we're at 000020, And so this is deep in the monitor. This is actually the monitor program that we're running. It does a restart 7. So it's going to jump up to 0, 0, 0, 0, 7, 0. So when we press the single step to go into that one, we can see that it pushed 0, 0, 0, 0, 2, 5 onto the stack. And now the new program counter is 0, 0, 0, 0, 7, 0. And we're cruising through that program. So this is just that program going along, and it's waiting for an input from us, basically. But what we're going to do is we're going to exit out of this loop, which basically means when we go back one step in the program counter, it's going to go back into the single step mode. So let's press an E. You can see it continued that last little loop until it had a return, and our stack pointer went down by 1. We're now at S equals 1. But we're still in the program monitor. So let's go ahead and press E again to get out of that. Now we're back to our program. We're back to the next part of our program, which is the increment L. So let's look at the L. Right now, L is at 221. We're going to increment. That's our HL pointer. L is now 222. The memory address 010222 is represented as M, which is 012, which is our line feed. We're going to decrement E, meaning that we put out 1 character. E goes down to 016. Now we're going to jump if a false 0. So if 0 is not set, we're going to jump back up and do the next program. And we can look that our 0 is not set because it's a lowercase down there. So when we do a single step again, we're going to jump back up to 010206 and do this loop again. So here we are at 010206. It's going to get whatever is in the memory location, which is our line feed, put that into A. We then set the most significant bit, just like we did before. We then move that into B, ready for the output. Do a restart 2, which is going to output that character. But we've already done that once. I don't want to do that again. So what we're going to do is put a breakpoint in the next line, that increment L, so that we don't have to go all the way through that and exit back out again. So let's do a F6, which will allow us to put in a breakpoint. The breakpoint we want is at 010213. We can see it changed colors there. So it has set that as a breakpoint. And now we're just going to let it go full speed until it hits that breakpoint. We did a G, and so now we're at that increment L point again. We can now single step through it. Single step, single step. Still a false 0, so we're going to loop, single step, go all through this. I get to the reset 2. I don't want to do that again, so I'm just going to press a G, let it do that, run at full speed. And we've probably learned about as much as we want to in this little bit. So instead of single stepping, I'm just going to press the G to let it go full speed until it hits that breakpoint again. So here's 1 G. It's gone around the loop. E is now 14. And we can see that we've output on the screen the HE. Another G, let it go around the loop again. 13, 12, 11, 7, 6, 5, 4, 3, 2, 1. So now E is equal to 1. Let's go back into single step because the next command, we decrement E. E is right now 001. When we decrement E, it's going to go to 0, and as soon as it does, our 0 flag is going to get set. There's our 0 flag got set. So now jump if false 0 is no longer true. It's not going to jump because 0 isn't false. 0 is now true. So the program is going to fall through and do the restart 0. So we single step one more time, and we're on the restart 0. What restart 0 is going to do is put it back to the monitor. So we press a single step here, and you can see we're back at 00000, and so the monitor is just starting from scratch again. We could single step through that all we wanted if we wanted to see how the monitor works. All right, what we're going to do is press a G for run at full speed. Now we're running at full speed. We can do an XQT 010200, and what it did was our breakpoint was still in there. So it ran this program until it got to our breakpoint and it stopped again. And so now we can go back and watch everything happen step by step, just like we were doing before. we really have to appreciate some of these tools that are out there. This is just a fantastic tool to be using and simulating the Mod 8 for when I'm writing code for the Mod 8 and I am looking for a bug or something. The simulator is just really a great way to see where the program is going. So we really have to be thankful for these tools, and the same with Herb Johnson's assembler that has the split octal output and the old mnemonics. All right, well, that's all I wanted to do for this video. I just wanted to focus on this Mod 8 simulator because it is such an amazing tool. You now have the capabilities of writing a program in an assembler for the 8008, either hand assembling that or using Herb Johnson's assembler to machine assemble that. You take the hex output file of that, and you can directly read that into this simulator so that you don't have to code anything in. Once it's in the simulator, you have the capabilities of running the program, single-stepping through the program, modifying registers, modifying memory values, and simply playing with this with an extremely powerful tool. So I would encourage everybody to do that. In the next video, we're going to look at the last of the assembler directives, and we'll look at some examples at how we do that and just some general examples of assembly code. And basically at that point, I think we'll be done with this. That's all I have for this video. I appreciate you watching. If you have any questions, let me know. But I really encourage you to go out and write some assembly and bring it into the simulator and just have a good time with this. It's a really some powerful tools and lots of fun wrapped up in this. Okay, thanks for watching. I will talk with you later. Bye-bye.